Okay, let's get started. Normally, I do this in a full lecture theatre, so you're going to have to pretend to do this or do this with someone in your household now. We're going to play a game. It's a game of two players, player A and player B. Player A guesses a number from 1 to 256, and player B can ask yes/no questions of player A. Each question costs a point, so it's a bit like hangman. So for example, a question might be, is it 340? No. It's like, is it 34? Yes. Okay. So I want you to sit down now and play that game. Okay, stop. Here's a new twist. I want you to write down your method that you've figured out as pseudocode. And then once you've done that, if you're playing with a partner, I want you to swap methods. So player B has done the same kind of writing down, and you're going to swap around. So you're going to play the game again, but player B can be pedantic as they like with your pseudocode. Okay. Try that again, and then enter in the pseudocode in the box below. Okay, so here's a couple of samples. Normally when we're doing this live, I give out prizes for whoever gets the best, quickest algorithm, the ones that happens in the most quickest time, and for the slowest and most rubbish algorithm. But we can't do that online, which is a shame. It's normally quite fun to do. So let's have a look at this. We could start off with a very simple example of the pseudocode. We could say repeat forever. Guess a number from 1 to 256. Ask, is it X? If the answer is yes, then stop, that's the solution. And there's different ways we could write this out in pseudocode, but they all do the same thing. They just say, is it 1? Is it 2? Is it 3? Is it 4? Is it 5? We're guaranteed that that's going to get the correct result. It will find it. If it's a number between 1 and 256, it will find that number. But it does feel a little slow, doesn't it? So let's look at the brute force approach. Now, brute force is a technical term we use. It's not the name of an elite team. It's not the name of a man who's half man, half lizard. It's generally the solution that's not pretty, it's not fast, it's not clever, but it will get the job done eventually. Don't reject the brute force approach. In an interview, never skip the brute force approach because you're too clever. Start off instead by saying, well, the brute force approach would be to try every combination, or start from the beginning and work the way through the list. When you're coding, it's often useful to code the brute force approach. It's simple, and typically it's going to work. What it does is it provides a gold standard against which you can actually assess your more elegant system. It's also a good way, it's something you can share, particularly if you're using object orientation and encapsulation. You can share that result with the rest of the team because it won't take you long to program and you know it's going to work. And then you can start working on a more elegant approach, which is hidden by the object. And then you can use it to test against the elegant system later on. And we should always remember the solemn words of Donald Knuth. We should forget small efficiencies, say about 98% of the time. Premature optimization is the root of evil. So again, engage and do brute force to begin with, and then get smart later on. Or, as Yoda would tell us, root of all evil, premature optimization is. So let's look at the fast or the smart way. This is probably what you did. And you started with the range. I'm going to do a range of 16 because 256 doesn't fit on the screen. And let's say we guessed 14, and you'd start with the top and the bottom, and you probably guessed halfway through. So we divide it 16 by 2, we get 8, and we say, is it greater than or less than 8? So you ask basically, is it above or below the midpoint? If the answer is above, we now know it's between 8 and 16. So we can forget about looking at all the numbers less than 8. Then what we do is repeat. We ask again, we find the midpoint between these two numbers. which is going to be 12. And then we say, is it greater than or less than 12? In this case, yes, it is greater than. And then we repeat with a new range. We say, is it greater than or less than 14, which is halfway between 12 and 16? But then we get some interesting specifics, which let's not worry about at this moment. We say, is it greater than the midpoint? So we say no. And then we repeat again. So we say basically halfway between 12 and 14 is 13. Is it greater than that? Yes. So then when the upper and lower range meets, that's the number we're guessing. That's probably the bit you were stumbling over, but when you're programming, you need to have that kind of follow through at the very end to make it all work out neatly with the minimum amount of code. Okay, that algorithm worked for numbers from 1 to 10. But what happens if they're not evenly spaced out? What happens if those numbers are like 1, 5, 14? There's gaps in the middle. Could we still do the same thing? Why not try that now? Good. You've found that you can still play the same guessing game in that list. So if you have an ordered list of numbers or strings or anything else, what we can actually do is find the one we're looking for very efficiently without stepping through that list. Congratulations, you've invented binary search. Wasn't that difficult, was it? When you were doing it for yourself, it seemed kind of easy and straightforward. Many of you just jumped straight to that and bypassed the brute force approach completely. Is that what you would do if you were programming though? If I said to you, program find 34 in this list and return the position in the array of 34, would you have jumped to that? So technically, we've just done binary search. Now, here's a couple of bits of history. What we've done there is we've created what's known as an algorithm. An algorithm is a well-defined procedure that allows a computer to solve a problem. Another way to describe an algorithm is a sequence of unambiguous instructions which achieve a specific aim. That's a pretty vague description, but it actually encompasses everything an algorithm is. The word algorithm goes back to a 13th century Persian mathematician called Muhammad ibn Musa al-Karim. I think I've got the pronunciation right, and if I've got it wrong, I apologize immediately. This was a very interesting step in the history of mathematics because al-Karim believed that mathematics was for everybody, and he wanted to create solutions that everybody could do. So before that, if you had a problem, you really needed a professional mathematician to do it. But he believed anybody could be taught simple sets of instructions that would actually get to the correct result. And that's what we want when we want to create a computer program. We're democratizing that logic. So if I asked you, what is the index of 73? How would you go about doing it? Yes, you'd use binary search, and you could probably program that algorithm. And here's the pseudocode for that algorithm using just loops. And here is the same code written in Java. Now, one of the important lessons to learn here is a good algorithm is a good algorithm in any languages. Just as your binary subdivision method was the best way to guess that number in spoken language, it was also the best way to do it in Java, it was the best way to do it in C++. And all algorithms these days typically are available in different languages. There's typically a library that does it for you. So you've got the C++ standard template library, Python has a library, PHP has a library, JavaScript has a library. All you have to know is to go out and search for it. So, binary search in the real world. Let's have a look how you'd actually do this. Now, 20 years ago, you'd be getting these books off the shelf. These are Knuth's Art of Programming, and they're kind of like the Bible for algorithmic code. And he goes through all of the details here. Unfortunately, in those days, in order to actually understand all this code, it was all written in assembly language, and it was all written using an invented assembly language called Mix, which is one that Knuth invented specifically for the purposes of publishing. These days, we'd be a bit simpler. We'd use an off-the-shelf solution called Java collections. So here's how you would do binary search in Java collections. You'd import Java collections as an import. You'd use the library. Let's invent our list. And then we just say arrays.binary search. That's that section here. The array and then the number we're looking for. And it will return to a number. And the index is one of two things. It's either the index of this number, 9, so 0, 1, 2, 3, 4, 5, it will return 5. And if the 9 isn't there, it will return -1. If you've got a Java compiler available to you, why not try typing that in now? So collections in many ways like Lego bricks. A program typically is one collection or another collection and calling algorithms on the collection to operate efficiently rather than doing the code yourself. Sometimes you have to do the code. There's no other way. There's no actual freely available algorithm. But quite often your programs are actually just assembling these predefined algorithms together. And doing that, you work efficiently. So with collections, you no longer have to write the tricky code yourself. You just have to be able to choose the right tool for the right job, unlike this guy. Here's a quick interview question for you while we wind up. In the interview, the guy's going to say, why does this code break? Try answering the question now in the box below. So, welcome back. So why does this not work? Because obviously the numbers are not in an ordered list. They're not ordered. So therefore we can't use the binary subdivision technique to actually go through that list. We'd have to go through it sequentially. And therefore, if you did give that to binary search, it would just break. And that's one of the reasons we haven't taught these things to you before, because in order for you to understand these things, you really have to understand how they work, not just what the name of the function call is. So not only does binary search work for numbers, it also works for objects. So for example, if I have an array of strings as a list, I can actually use collections.binary search. So we have arrays.binary search to search an array, and we have collections.binary search to search a list. So here we go. Here's how you might see it used with an object. So now we've got an array of kidney patients. It doesn't really matter. We have a kidney patient class, which has some information about it. And then we use binary search to go through the list. There's a problem there, which is we need the object to be comparable, because you need to answer the question, is this bigger than that? In order to do that, we have to add in two things. We have to make the object that we're going to be searching on a subclass of comparable. So it must implement the comparable interface. And to do this, it must override the compare to method. And what this does is it basically says, how do I compare this to that? Is this kidney patient higher or lower in this list than that one? And with that, we can then find the kidney patient from a binary list. So let's have a look at this in practice. You have a name in an alphabetical list, and you want to find the name, is it? How would you go about doing this? Well, obviously what you would do is you would do binary search. But now here's another question. You have two arrays, one of which is the array of names, which is ordered, and the other one is an array of, let's say, phone numbers. They're not ordered. They can be anywhere. And for every person in one list, there's a number in the other list. So for Carol, we want to return 355, and for Rick, who isn't in the list, we want to return -1. How would you go about programming that in? That's right. What you would do is you would search for the person using binary search, and then you would find the index and use that index in the other array to actually return the number. So if I was looking for Barnaby, I would do the binary search to find that Barnaby is at index 2, and then I would look at array 2 to say that the value for Barnaby is 985. And that's the kind of way that interview questions get asked. So You can realize once you've understood how to do something like binary search, you can then use binary search to solve other problems that are more tricky and more complicated and you might not have a clue to begin with. So once you can know one algorithm, you can solve many different problems with it. Okay, we're about finished up here. Finally, what have we learned? We've learned why we're learning about algorithms and computer science. We've actually looked at binary search. We've realized that not all algorithms are created equal, but we're doing that more in greater depth next week. We've learned what algorithms are, and we've learned about pseudocode. So next week, performance, or 5 ways to make your code fly. Thanks very much.